Okay, so I'm going to finally finish up the notes for double slit diffraction and interference, focus on diffraction gratings. I forgot that we talked about this in class, but I hadn't formalized the notes. So this is the last page of the double slit stuff. Okay, so we're going to talk about multiple slits. In other words, a diffraction grating, which we use in the lab to help us figure out wavelengths of different color light. So let's take two different cases. We have thousands of more slits added alongside existing slits. Right? The other case is we're going to add 1,000 more slits between existing slits. Okay, so in other words, if I have existing 2 slits now, in the first case, we're just going to add more and more and more. That's what the alongside means. So what is important about that is the distance between slits. D remains unchanged. Okay, so we showed what the pattern looks like. So first of all, since D doesn't change, the fringe angles remain the same. Okay, you're not going to get interference patterns, the fringes, to get further and further apart. But the peaks are going to be much sharper. Okay, in other words, you're going to have a narrower width. And since you have more light that can pass through, the bright spots will have a greater intensity. So we can see that contrasted right here. So this is the case where we have normal double slits, right? That's double slits right there, or 3 or 4. Here is multiple slits where D has not changed. So you can see that the peaks line up over each other. So the angle hasn't changed, but it's much sharper and it is much taller. Okay, we talked about this is easier to understand simply because there's more light. Why it's sharper, it's a little less obvious, but if I try to do just more slits and I draw a screen here and I have light meeting here from, let's say, 4 slits, there's going to be more cancellation. Excuse me, at this spot you're going to have a very sharp, right, they all have to be in phase, but if I move off of this just a little bit where the waves meet, they're going to have more waves are going to meet out of phase than prior, so you're going to get a steeper decline or decrease in intensity as you move away from that sweet spot of path difference being integer of the wavelength. Sorry. Okay, now let's take the other case where we add more between them. And this is really what happens in a diffraction grating, right? In a diffraction grating, you are reducing D tremendously. And the easiest way to do that is just within a certain space, put as many slits as possible by etching in very, very, very narrow lines. Okay, so I have it summarized here. The fringes are still going to be very narrow and brighter, but the diffraction angle is now going to be much greater. Okay, and again, we know why that is. Therefore, you can no longer use a small angle approximation. Remember, small angle approximation say sine theta equals tan theta equals theta in radians when the angle is, 5 or so degrees less. So the angles, as you've already seen, is going to go up to 20, 30, 40 degrees. Therefore, you must calculate the wavelength in 2 steps. Okay, in other words, we could use the diffraction pattern. We could say sine theta equals x over big D, and then knowing x and d, we can get theta. Then we can say sine theta equals lambda over d and define the wavelength knowing the angle. Okay, well, I guess I summarized that right there. So we just have a simple example here. I'm just going to set it up. We have a diffraction grating that has 500 lines per millimeter. So D is simply going to be 1 over that 500. And that's going to give us an answer in millimeters. You just might have to convert it to meters. Okay, so that's pretty straightforward. Angle. Okay, so what do we know? We have the first fringe, that's x. The screen is 100 centimeters away. D, they're in the same units. So I could simply say tan theta is x over d, which is 10 over 100. Okay, which is 0.1. I don't know what the inverse tan of 0.1 is. You can work that out, but it's pretty straightforward. And then I can say lambda is going to be equal to d sine of the angle we found above, where D is the answer here and angle is the answer there. So that sums up what you get from diffraction grating, and I think it's worthwhile if I back up a little bit, look to be able to contrast these 3. So this is double slit, maybe 3 or 4. This is a diffraction grating. Let's call it a grating, which is many, many slits. And this in the bottom is a single slit. okay, which by now, well, maybe we haven't learned. Depends on when I approach this. So understand the similarities and the differences among those three cases, and hopefully understand why that is.